Yes, and here, this is an example of what I'm talking about. We need to have control. Look at this. This is an automobile car. And for example, we know that during automobiles, we have a lot of gas emissions, right? And we have this climate change that we are having. Every car is producing some emission that is affecting the ozone layer. So what material scientists and engineers have done is that to create a catalytic converter here, through the understanding of imperfections in solids, we have created some catalytic converter to convert these gases emissions so that they cannot destroy the environment. So this is exactly what I'm telling you about. That's why you need to learn imperfections in solids, because when you learn this, you can able to control these situations so that we can reduce climate change. Let me give you an instance. Here is the gas. This is the poisonous gas. Here is the car. The gas is coming out from here. We get this catalytic converter. This catalytic converter, what materials are they made of? It's made up of steel, and it's made of a ceramic material. You can see that, and here is the insulating package. So the gases, the carbon monoxide, we know carbon monoxide as a poisonous gas, and we have other nitrogen oxide. So they can go through this catalytic converter, and upon here, they have to undergo some chemical reactions. The molecules of these atoms can stay here, and upon this process, they are undergoing some chemical reactions. And these chemical reactions you should know, because this is made possible because of atomic defect that we're going to see. So then what happens, the gas will come out here as form of water or nitrogen. So that's why you see now cars, when they run, what happens? You see some little water is coming out. So this is the beauty of understanding imperfections and atomic defects. And one other examples also will be in our mobile phones, in our computers, in our household machines, everywhere. If we understand right from the atomic level the importance of understanding imperfections in solid materials, then we can able to design materials to meet our daily needs. We can able to control these materials. So that's why we should study imperfections in solids. And these dictate the properties of materials, and we know that whatever that dictates the properties of material, you should know that you should be able to study these properties, these structures, and how these materials are performed. And the only way we can able to manipulate this is for us to be able to study these things. So here is our learning objective. What are our takeaway? What can you take home with you when you study material science and engineering, and especially chapter 4, imperfections in solids? So, number one, you should be able to describe what vacancies and self-interstitials are. I know most of you are familiar of what vacancy is, right? When you're looking for a job, for example, you go out there, you search for a job, get a job, and upon this job, when you are looking for a job, you have vacancies. Alright, all along we talk about chapter 3 as we know about polycrystalline materials and single crystal materials. And we said that materials are perfect, but this is wrong. There is no material that is perfect that doesn't have some vacancies. So we're going to see vacancies and self-interstitials, and we should be able to calculate how many vacancies are present in every material, how many defects are in there. So you should be able to know that, and you should be able to calculate these things, because only then you can able to control how these vacancies affect the properties of these materials. So you should be able, so that's the takeaway we're going to take with us at home after we finish studying this course. Another thing is the solid solution substitutions. We have, like, for example, a simple analogy with water. If you are mixing water with alcohol, you cannot be able to differentiate it until you taste it. Then you know that yes, there is mixture. So it's the same thing with solid materials. We can mix two solid materials. We can mix copper and zinc to determine that. And another thing will be the masses. How can you calculate these masses? Because it's very important. So for example, if you mix copper and zinc, you want to know how much of copper do you have within this material and how much of zinc. Because when you combine these two, you have alloyed material. So you should be able to determine the weight, or you should be able to determine the number of atoms that are within this material. So that's the takeaway we should have. Another takeaway will be defect. We have edge and screw defect. So you should be able to calculate these things and mix defect. So only then you can able to understand these imperfections and then try to control these imperfections. And we're going to talk about great boundary and twin boundaries. These are very, very important things because we know as human beings we have what we call twins, right? This is the same thing that is happening in materials. So this will even help you some kind of analogies to understand what is happening in our life. Now we start with vacancies. Here is a typical example of vacancy and interstitial. A vacancy is, if you look at the atoms are arranged in a period. But however, if you look at this point here, an atom is missing here. So when an atom is missing, we say there is a vacancy. And in some cases, these atoms, you can find them somewhere else. If you look at here, there is an atom here. Here, the atom not supposed to be here. So this we call self-interstitial. And why we call it self-interstitial? Because this atom that is here is the same as these other atoms. But here there is no atom where there's supposed to be an atom. So we say these are vacancies. And within a material, we should be able to calculate how many of these vacancies are here. So how can we do that? First, we need to come up with some mathematical equations to do that, to calculate the number of vacancies. And this we need to have little knowledge of thermodynamics. And the principles of thermodynamics is just the measure of entropy. And entropy is just randomness, how things occur randomly. Because now with this vacancy, what happens is that because the atoms are vibrating, the atoms will try to occupy this space. And when an atom comes here, the vacancy will move over there and the next atom. So we can calculate these vacancies. So that way we come up with this formula mathematically. And this is a very simple formula. To calculate the number of vacancies within a material, all you need to have is the number of interstitial sites under normal conditions. If we assume that the material is perfect, how many lattice sites this material have? And then you have the exponential value of QV over KT. QV is just the energy that is required to remove one atom within the lattice site, because this is measured in electron volt. And K there is the Boltzmann constant, which we can talk about. But the purpose of this is not just to memorize these things, but rather to be able to come up with these things. It's assuming you are in the middle of the forest, you happen to have copper and zinc. So you should be able to come up with these calculations to calculate how many percent of copper and how many of zinc is there, and how many vacancies are available. So that's exactly what we are doing here. We are calculating the equilibrium number of vacancies of copper. And of course, the temperature is very, very important. At what temperature? Because we know that when the temperatures are higher, you should know that then we have randomness. We have some higher degree of randomness. So this is the mathematics, but we are not going to worry ourselves today for this mathematics. We just want to understand the basic concept of imperfections in solids. And we talk about solid solutions, solvents. When we have, for example, I said earlier on, zinc and copper, you should be able to know which one is the solute and which one is the solvent. And for example, if we have a complete material that is in copper, let's say for example, and 100%, or let's say 99.999%, because you can never have a material that is 100%. You can have material that is 4 decimal places percentage, as this is how far we have tried, but you can maybe help with some sophisticated technologies to have more pure material. But pure materials are always soft. So if we want to enhance the mechanical properties, we need to deliberately put some other atoms of other material, impurities within this material, and then we take zinc. So if we have 70% copper and 30% zinc, what will happen that this material become much stronger comparing pure copper. So copper is weaker, and this will make the material become more stronger. And so copper here will be the solid, and then solvent there will be zinc. And this we call brass today, which is 70% copper and 30% zinc. And we have some rules. If there is no rules, there is nothing that exists. We should have rules. And exactly in material science and engineering, we also have some rules. We talk about atomic size factor, how size the atom is. So supposing here, you see this atom is green. but the other ones are blue. But this can substitute for these other atoms. Why? Because the atoms, the sizes are the same. So we call this substitutional solid solution, because the size of the atom is the same. But when the size of the atoms are different, for instance, here, you can see these are much bigger than this. So this we call interstitial solid solutions. So atoms are occupying an interstitial position. Remember when we talk about the FCC, BCC crystal structure, we talk about that. And this is a FCC crystal structure. Look at where the atoms are residing, at the corners. And when atoms reside here, this is FCC, we say these are octahedrals and these are tetrahedrals. And then with the crystal structure, if the element copper having FCC and the other material having another crystal structure, then it's not going to work. There are going to be some lattice strain. So to avoid those strains, what we do, we ensure that the materials both have the same crystal structure. Another rule of thumb is the electronegativity. We want to ensure that these materials have the same electronegativity. And also the valencies, number of valencies that are present in the material. So these are the things that we use to calculate these things. And of course, the specification of compositions. I'm going to leave the mathematics for now, just for us to understand the concept. Because when you understand the concept, the mathematics is easy. So this is just to calculate in terms of atom percent on weight percent. So when you are able to manipulate this to transform from one conversion to another, from atom percent to weight percent, or weight percent to atom percent, because you want to know how many copper are present within this totality of this material, or how many zinc are present there. So we can use the composition in terms of weight percent, which we have here, or in terms of atom percent, which we have here. So we're going to stop here for today. Next, we're going to see how dislocations and linear defects affect materials. So take this course seriously. Go over these things. I'll send the slide so we take a look at these things. Until then, have a good day. Goodbye.